Flashing red lights, cybersecurity for intelligent transportation systems. Red lights, yellow lights, green lights. A flashing light? A traffic warning sign? Recognized as a critical infrastructure by the Department of Homeland Security, DHS, the transportation system is essential to modern life. From the skies to the seas to the railways to the roadways, and to bike lanes and pedestrian crossing, this highly complex network safely and efficiently connects and feeds us all. Within this network, the often unnoticed traffic control systems, TCS, and traffic management systems, TMS, ensure that everyday routine travel and commerce are conducted safely and hopefully efficiently. Traffic management systems, TMSs, aim to reduce traffic congestion and its related problems. To this end, TMSs are composed of a set of applications and management tools to integrate communication, sensing and processing technologies. Traditionally, traffic engineers have used a combination of two approaches, passive and active. As the traffic design, management systems, technology and the discipline have evolved, the integration of intelligent traffic control and management has occurred. This evolution has opened up the field of traffic management to a vastly larger number of potential cyber threats and vulnerabilities. Passive, active, and intelligence traffic control systems and traffic management systems. Traffic management has never been a static discipline, for it has continually adapted to societal changes. Today, the changes seem to be constant. The discipline has moved from passive to active systems and is beginning to transition into intelligent systems. From colonial times until recently, roadway toll lanes were initially set amounts in static locations. Stop signs and pre-programmed signal lights helped the industry evolve. These were relatively passive. The introduction of Easy Pass and roadway weight sensors for commercial trucking began the adoption of more active measures. With roadway sensors, dynamic toll pricing, and a wide variety of other devices and techniques, the industry is moving toward what is termed intelligent traffic management. Passive traffic control systems and traffic control management. Passive traffic control systems, TCS, includes the design of the roadways, the laws that govern them, and the devices. A passive roadway design approach assumes, and strives to account for, the worst-case scenario, both in terms of user behavior and traffic congestion. For many years, roadways have been designed with a passive approach, allowing drivers to travel unpredictably at high speeds. Passive devices provide static messages of warning, guidance, and, in some instances, mandatory action for the driver. Passive traffic control devices identify and direct attention to the location of a highway rail grade crossing. Passive traffic control devices consist of regulatory signs, warning signs, guide signs, and supplemental pavement markings. In a passive state, a controller maintains functionality in the absence of connectivity to the rest of the traffic control network. The functionality may be directing traffic as programmed, providing local responses to emergency services and public transportation, or remaining in flash operations in case of emergency. Within a passive state, a light can function without data collection and/or monitoring status. If any traffic light is dark, without power and not flashing, the intersection impacted must begin always stop operations until local law enforcement is present and the signal is operational. 4. Circumvention of these routine controls can easily lead to public endangerment. Active traffic management systems and traffic control systems. Active traffic management is the ability to manage recurrent dynamically and non-recurrent congestion based on prevailing and predicted traffic conditions. Active traffic control systems, TCS, include adaptive ramp metering, adaptive traffic controls, reversible lanes, and traffic control software that can adjust traffic patterns in real time. Intelligent traffic control systems and traffic management systems, intelligent transportation systems. The introduction and integration of sensors and IoT devices, under the title of smart mobility, fostered a maturation towards an intelligent traffic control systems, TCS/traffic management systems, TMS, infrastructure. Intelligent transportation systems, ITS, is the much closer integration amongst all of the traffic management components: pedestrians, bikes, drivers, automobiles, buses, public transportation, and the traffic management system. This integration allows for autonomous vehicles, adaptive traffic, and efficient roadway travel. It grants a way of sensing, analyzing, and communicating amongst the technologies intended to improve commuter and pedestrian safety, mobility, and efficiency. It utilizes adaptive signal systems, driver advisory and route planning in automated vehicles to increase the efficiency of the overall system. With the integration of the advanced traffic controller and other external components, emergency and public transportation services have benefited from its use. For instance, a public bus can extend the green light time, allowing for additional bus clearance called transit signal priority. Transit signal priority, TSP, uses a location-based wireless communication method that sends a signal to the traffic controller to process changes to a movement phase. These systems are designed to remove congestion and increase traffic flow, resulting in a reduction of travel times and likely reduce the carbon footprint. For example, a preferred vehicle, i.e., public safety vehicles or public transportation, may be located and identified on the road. With that identification, the corresponding traffic controllers could be changed to prioritize the bus route. Many of these services also reduce cost for infrastructure expenditure. For example, the City of Tampa reduces on-call signal technician hours significantly since the installation of their active traffic management software or the establishment of the EasyPass system that automates payment services for express highways. Protecting intelligent transportation systems. How important is a roadway sign that notifies motorists that construction is present? How can an ambulance be denied their preemption on the way to save a life? Intelligent transportation systems, ITS, are considered the most vulnerable of all operational technologies. A mid-sized municipality is likely to have thousands of roadway devices that are not protected nor monitored. Intelligent transportation systems focuses on the monitoring and management of physical components and events that control industrial processes. This technology requires constant human oversight and near-perfect uptime. Most systems are typically monitored and operated by supervisory control and data acquisition (SCADA) systems. Some critical system sectors are constantly monitored and secured at the physical level. However, the localities and industry often fail to protect these systems and traffic management devices and networks. Traffic management operations and engineers frequently do not fully realize and address the risk of vulnerable traffic systems and processes. Municipalities must seek to increase investment improving traffic cabinet security, traffic roadway network infrastructure, and reduce cyber and physical threats to traffic control systems. In many ways, through traffic control improvements, the creation of procedures, and tasking ways bad actors can exploit the systems, smart mobility divisions can provide an opportunity to a more safe and secure connected traffic system. In the past, scheduled maintenance operations provided a sense of safety and compliance of all operation technologies, as the maintenance periods allowed engineers a time to review and revise the implemented policies and technologies. However, in the connected age of infrastructure and the establishment of smart cities, cyber threats are more prevalent. Traffic systems no longer have isolated network topologies, and the threats arrive faster than the scheduled maintenance periods. As cars gain the ability to talk to the infrastructure, the implementation of wireless transmission and other traffic control components, traffic management operations, and cyber analysts must support the security and design of traffic systems networks. As smart cities emerge, traffic systems become even more crucial. There will be more need for traffic control safety, integrity, and reliability. The primary goal of traffic engineering is to provide a safe, efficient, and convenient way of movement of persons and goods. To consistently achieve this goal, the standards of traffic systems design must evolve. As technology continues to integrate into traffic systems, new secure interactions between systems must ensure that the systems are designed to withhold its fail-safe mechanisms in the face of an attack. Traffic Safety First Design Principle. For a traffic signal to be a danger to public safety, the hacker must be physically at the traffic signal cabinet. A traffic signal cabinet has a controller that is considered the brains of the traffic signal. The controller is usually the device that connects to the OT network infrastructure. A traffic signal controller can be subject to exploitation. Still, the risk of public endangerment is considerably low due to the traffic signal possessing a conflict monitor known as a malfunction management unit, MMU, separate from the traffic controller. If programmed correctly, the traffic signal controller should not create a conflict in the MMU and the functions it has embedded in it. Safety components of a control system infrastructure must be monitored and logged accurately. Data provided by monitoring and logging the system state, trends, and actions can involve parties to make predictions, investigate system issues, and establish needed action. This acquired data is utilized in the active traffic management system and supports department decisions. When traffic engineers introduce the adaptive traffic system, it can only be effective by relying on factual data for the AIR system to adjust traffic patterns, provide analysis, and check for anomalies. If an attacker is in the system log for an amount of time, the data it collects could affect traffic commute times, research data, and possible funding for the infrastructure. With the inclusion of connected/autonomous vehicles, roadside unit, RSU, and onboard units, OBU, many vehicles will have access to external communications, including the infrastructure. According to the threat model conducted during a 2017 study using falsified data, there are 4 possible traffic control attack surfaces: traffic signal controllers, OBU, RSU, and vehicle detectors. Based on the attacks, the article identified direct and indirect attacks. Indirect attacks are more likely to be conducted. 6. With many wireless technologies exposures, the impact could likely impact falsifying data, slowing network performance, and maximizing system delay. In an urban transportation system, a falsified data attack can enable a vehicle detector to activate when a vehicle is not present or move the detection zone to prevent the traffic face from being activated if a vehicle is there. Of course, this will cause significant traffic delays, which could cause commuters to make risky traffic decisions. An indirect attack on vehicles could also allow attackers to disable vehicle safety features in the surrounding smart mobility infrastructure. The attacker could spoof the OBU within the infrastructure to act as if a pedestrian is not crossing the street by disabling sensors or MAC addresses of phones. These categorized attacks could cause severe injuries and present bad publicity, setting the autonomous vehicle program back. Wireless radio represents the traffic management center's connection, which could be fiber, copper, or other communication methods. The traffic controller directly connects to the switch, and the MMU connects to the controller. With an MMU, there is a smart monitor card. This smart monitor card is intended to guarantee that no phases can conflict with another unless soldered physically by a technician. For example, if the traffic signal controller is hacked and taken over, the MMU makes sure that the controller prevents any violation of the traffic signal and places the traffic signal into a malfunctioning flash. Although it may not directly impact public safety, a failure of a control system or a denial of service, DOS, could cause issues. If a breach or attack denies the ability of these services to utilize the traffic systems efficiently, these services could create great misfortune.